All right, welcome to another deep dive where we, kind of roll up our sleeves and really get into some fascinating source material. And this one, I think, is going to be particularly interesting for you, especially given what you told us about how you like to learn.
Yeah, you mentioned that you really enjoy getting a solid grasp on complex topics, quickly, but without sacrificing that depth of understanding.
Exactly. You want the insights, but you don't want to wade through a ton of unnecessary jargon or overly complicated explanations, and we totally respect that.
Absolutely. So today, we're going to do a deep dive into the world of Bruno de Finetti.
Oh, yeah, definitely.
Big name in probability and statistics. And specifically, we're going to be focusing on a 1993 paper by Sergio Wechsler that delves into some of his most intriguing ideas.
Okay, so Diffinetti, 1993 paper, sounds pretty academic. What are the big ideas we're going to try to unpack here?
Well, the paper really centers around de Finetti's famous representation theorem, which has some pretty profound implications for how we think about probability. But we're also going to be exploring the concept of exchangeability, which is a really crucial idea in de Finetti's work.
Exchangeability, right. I'm vaguely familiar with that term, but I'm sure a lot of our listeners are eager to hear a clear explanation.
Absolutely. We'll definitely break that down. And then we'll move on to something called predictivism.
Predictivism. Okay, now that's a term I haven't heard before.
It's a particular viewpoint within statistics that emphasizes the importance of focusing on observable data when making predictions and drawing conclusions.
Interesting. So we're dealing with some pretty foundational concepts in probability and statistics here. What kinds of sources are we working with to explore all this?
Primarily, we'll be relying on excerpts from Wechsler's paper, which is, a scholarly article, so it's a bit dense, but that's where we come in, right? To distill it down to the essentials.
Absolutely. We're here to make these complex ideas accessible and engaging. So what's the mission for this deep dive? What's the key takeaway we're hoping our listeners will gain from all this?
Well, our aim is to help you understand De Finetti's core arguments against what he saw as sort of arbitrary or unfounded statistical models.
Okay, so he was critical of certain ways of doing statistics. What did he propose instead?
He offered a different way of thinking about probability and statistical inference, one that's rooted in subjective beliefs and a careful consideration of the evidence we can actually observe.
All right, I'm starting to get a sense of where this is going.
And hopefully along the way, you'll have some of those aha moments where things really click into place.
Love those aha moments. Okay, well, let's dive in then. Right at the beginning, Wechsler quotes Stifinetti describing his representation theorem, and this quote really jumped out at me. He said it was essentially the fruit of a thorough examination of the subject matter, carried out in an unprejudiced manner with the aim of rooting out nonsense. So, he clearly wasn't afraid to challenge conventional thinking.
Right, he was very direct and passionate about his ideas. And Wechsler argues that this statement actually reflects De Finetti's broader philosophy.
Beyond just the theorem itself.
Yeah, it was a statement about his whole approach to Bayesian statistical inference and decision-making. It was about being rigorous, evidence-based, and not letting unfounded assumptions creep into your analysis.
Okay, that makes sense. Now, can you remind us quickly what Bayesian statistical inference is all about?
Sure. It's a way of doing statistics that explicitly takes into account our prior beliefs about something. So instead of just looking at the data in isolation, we combine it with our existing knowledge to draw conclusions.
Right, so it's like updating our beliefs based on new evidence.
Exactly.
And this leads us to one of DeFinetti's main concerns, right? Statistical models with these, what he called arbitrary parameters.
Yes, that was a big issue for him.
So what exactly did he find problematic about that? What was he objecting to?
He was essentially arguing against the practice of just assuming that certain parameters exist without any real justification from the data. Just throwing in parameters without a clear, direct connection to what we can actually observe in the real world.
Like making stuff up to make the model fit better.
Well, it's not always deliberate making stuff up, but sometimes it can feel that way.
Right, it's like you're adding complexity without necessarily gaining real insight.
Exactly. And De Finetti saw this as a problem, particularly in what's called the frequentist approach to statistics.
Okay, the more traditional way of doing statistics.
Right, where the focus is often on long-run frequencies of events. And in that framework, there's this idea of these fixed but unknown probabilities out there in the world, and we're trying to estimate them. Like there's this true value we're trying to pinpoint.
Right, like the true probability of a coin landing on heads.
Yeah, and Wechsler highlights how De Finetti saw this belief in these inherently existing probabilities and parameters as kind of a root cause of this tendency toward arbitrary parameterization.
Okay, so if you start with the assumption that these things are real, it becomes easier to just assume they're there even when the data doesn't really support it.
Precisely. And it's interesting because Wechsler points out that even some Bayesians can fall into this trap.
Oh, so it's not just a frequentist problem.
Right, and Diaconis, another statistician, suggests that it's partly because modern software makes it so easy to fit curves to data. You can get a good-looking fit without really thinking deeply about what those parameters actually represent.
It's like having a fancy hammer and then seeing everything as a nail.
Yeah, good analogy.
So if Definetti was so critical of this kind of arbitrary use of parameters, what did he propose as a more robust foundation for statistical modeling?
Well, this is where the idea of exchangeability comes in, which was absolutely central to his thinking.
Okay, let's talk about that. Wechsler describes it as an invariance judgment. What does that even mean?
So imagine you have a sequence of outcomes, like, say, flipping a coin 10 times. The results are exchangeable if the order in which those outcomes occur doesn't change your overall assessment of their probabilities. So you'd assign the same probability to getting heads, tails as you would to getting tails, heads.
Okay, so it's about the symmetry of our beliefs regarding the order of the observations. It doesn't matter how we shuffle them around, our fundamental beliefs about the underlying process remain the same.
Exactly. And Definetti argued that parameters should only be considered in relation to these kinds of invariance judgments. If you can't justify a parameter based on some observable symmetry in the data, then it might be arbitrary.
Okay, that's a pretty strong stance. And this leads us to the concept of predictivism, right?
Yes, predictivism builds on this emphasis on observable data and invariance judgments. It essentially says that statistical inference should primarily focus on events that we can directly see and measure.
So instead of trying to construct elaborate models of some hidden process, predictivism is about making predictions based on what we've already observed.
Precisely. Cifarelli and Regazzini, two statisticians who built on Definetti's ideas, describe predictivism as a non-hypothetical approach.
Non-hypothetical, okay. How does that contrast with the more traditional view of statistics?
Well, the traditional view often seeks to uncover the underlying probability mechanism that's generating the data, like figuring out the true probability of a coin landing on heads. Predictivism, on the other hand, says let's focus on making coherent predictions based on the data we have without necessarily assuming some specific underlying mechanism.
It's like saying, we might not know exactly how the coin works, but based on what we've seen so far, here's what we predict will happen next.
Exactly. And Cifarelli and Regazzini, following Definetti, saw statistical inference as basically a consistent methodology for making these previsions, or predictions, conditional on the available data.
So it's all about making those predictions in a way that aligns with the evidence. Does this mean that predictivism rejects the use of parameters altogether?
Not necessarily. Wechsler clarifies that it doesn't demand the complete elimination of all parametric models, but he argues that they should be viewed as auxiliary tools, things that can be helpful once you've addressed that initial arbitrariness.
Okay, so parameters can still have a role, but they need to be justified by their connection to observable symmetries, to those invariance judgments we talked about earlier.
Exactly. They need to be grounded in the evidence.
Okay, that makes sense. Now, Wechsler transitions to talking about representation theorems. How do these fit into this framework we've been discussing?
Right, so representation theorems, in the context of Definetti's work, essentially provide a justification for having an opinion about a probability as a valid statistical procedure.
Okay, that sounds kind of self-evident. Why does that need justification?
Well, Definity was really challenging the idea that probabilities have to be objective entities that exist independently of our beliefs.
Hmm.
He was saying that our subjective beliefs about future events can actually be mathematically represented as if there were some underlying probability distribution at play.
So it's like formalizing our subjective beliefs in a consistent, mathematically rigorous way.
Exactly. But the key point here is that the initial choice of that representation, that initial opinion, is not dictated by mathematics. It's a subjective choice.
Okay, so the math helps us make our beliefs coherent and allows us to work with them in a rigorous way, but it doesn't tell us what to believe.
Precisely. And this leads to a very interesting philosophical point.
What's that?
Well, it means that Even though we might use probabilities and statistical models, we don't necessarily have to believe that there are these true objective probabilities out there in the world.
Okay, that's a pretty big shift in perspective.
It is. And it's one of the key insights that Definetti brought to the field of statistics.
Wechsler then brings up Dowid's work on something called analysis of variance, or ANOVA. How does that serve as an example of this predictivist approach in action?
So Dawid showed that you could actually derive the standard Bayesian ANOVA model by starting with considerations of exchangeability.
Okay, remind us again what exchangeability is all about.
It's about saying that the order of the observations doesn't affect our beliefs about the underlying process. So in the context of ANOVA, if you have, say, three groups you're comparing, exchangeability means you have no prior reason to believe that one group will behave differently from another. You're treating them as essentially equivalent.
Okay, so you're starting with this assumption of symmetry, of no inherent differences between the groups.
Right. And what Dawid demonstrated was that if you assume exchangeability, it naturally leads to a particular model structure with certain parameters. But as Wechsler points out, even in this predictivist derivation, there's still an element of arbitrariness in the assumption that the data within each group follows a normal distribution.
Okay, so exchangeability gets you part of the way there, but there might still be other assumptions that need to be made.
Yeah, it's not a magic bullet that eliminates all potential arbitrariness, but it does provide a more principled starting point.
All right, that makes sense. Now, Wechsler introduces another set of concepts, intersubjective models, and the idea of unanimity. What's the core idea behind these?
This is where Dewey really built on some earlier insights from Definetti. He introduced the idea of these intersubjective models, which are basically statistical models that a group of individuals using Bayesian methods would unanimously agree upon.
So it's like finding common ground in our statistical beliefs.
Yes, but it's a bit more nuanced than that. It's not just about everyone having the same prior beliefs. It's about agreeing on a model conditional on observing a sufficient statistic from the data.
Okay, what does sufficient mean in this context?
A sufficient statistic is basically a summary of the data that contains all the relevant information about the parameter we're interested in.
Okay, so it's like extracting the essence of the data.
Exactly. And the idea is that even if individuals have different prior beliefs, they can still reach a consensus on a model once they've seen this sufficient statistic.
Interesting. So the shared evidence helps us overcome our initial differences in belief.
Exactly. And this unanimously agreed upon model is what Dawid called an intersubjective model. It captures the shared understanding that emerges from the group's collective wisdom, you could say.
And this connects back to something Definetti himself said, right? About problems not admitting an initial opinion.
Yeah, Wechsler mentions this. Definetti suggested that these problems where everyone seems to agree from the start, these seemingly non-subjective problems, could actually be seen as multi-subjective problems, where there just happens to be a coincidence of opinions.
So it's not that there's no subjectivity involved, it's just that everyone's subjective beliefs happen to align in those particular cases.
Precisely. And Definetti even proposed that this idea could potentially bridge the gap between Bayesian and frequentist statistics.
Oh, really? How so?
He suggested that instead of seeing frequentist methods as fundamentally different, we could view them as a special case of Bayesian methods, where there's this very strong agreement among individuals about the prior beliefs.
So it's like everyone's prior beliefs are so similar that they effectively collapse into a single, seemingly objective prior.
Exactly. And this was actually a more moderate stance for Definetti.
How so?
Well, later in his career, he became much more adamant about the inherently subjective nature of probability.
Okay, so he went from this more conciliatory view to a more, you could say, hardcore subjectivist perspective.
Yeah, I think that's a fair characterization. He came to reject any interpretation of probability that wasn't purely subjective, whether it was based on logic or physical properties or anything else.
So he was really committed to this idea that probability is fundamentally a reflection of our beliefs.
Absolutely. And it's a view that has had a profound impact on the field of statistics.
Now, if we're embracing this subjective view of probability, how do we capture any sense of objectivity? It seems like those two things are in tension.
That's a great question, and it's something that Dawid grappled with. He built on Definetti's notion of a coincidence of opinions to develop a way to express a form of objectivity within this purely subjective framework.
Okay, I'm curious to hear how he did that.
His key insight was that even if individuals have different subjective opinions about observable events, they can still agree on a conditional probability given a sufficient statistic.
Okay, so we're back to this idea of a sufficient statistic capturing the essence of the data.
Right. And this unanimously agreed upon conditional probability is what Dewey termed an intersubjective parameter.
So the sense of objectivity comes from the agreement among individuals rather than from some inherent property of the world itself.
Precisely. It's a form of objectivity that emerges from the consensus of subjective beliefs. And this idea also leads to the notion of an intersubjective model, which is essentially the statistical model that everyone agrees on, conditional on observing this sufficient statistic.
So we're not just agreeing on a single parameter, we're agreeing on an entire model.
Exactly. And this intersubjective parameter, the point of agreement, can be seen as a maximal invariant.
Okay, yet another new term. What does that mean?
A maximal invariant is basically something that stays the same, something that's invariant, under the most general set of transformations that reflect the shared beliefs of the group. So it's like the most stable, the most agreed upon aspect of the model.
Okay, so it's capturing the core of what everyone agrees on, despite their potential differences in other beliefs. And exchangeability, the idea that the order of observations doesn't matter, is just one specific instance of this kind of invariance, right?
Exactly. Exchangeability is a particular kind of symmetry that can lead to an intersubjective parameter, but there might be other types of symmetries as well, depending on the situation.
Okay, that's helpful. Now, Wechsler provides a really interesting example involving exchangeability and something called rotational invariance. Can you walk us through that example?
Sure. Imagine someone whose beliefs about two random quantities, let's call them x and y, are such that they believe these quantities are exchangeable.
Okay, so the order in which we observe x and y doesn't matter.
Right. And let's say they also believe that their beliefs about x and y are invariant under rotations around the origin.
Okay, so if we imagine x and y as coordinates on a graph, then rotating the graph doesn't change their beliefs about the relationship between x and y.
Exactly. Now, in this scenario, it naturally follows that their main focus would be on the distance of the point, xy, from the origin, rather than its specific position on a circle of that radius.
Right, because all the points on a circle are equivalent under rotation.
Precisely. And in this case, the intersubjective parameter, the thing that's invariant under these rotations, is the squared distance from the origin, which is calculated as x set plus y.
Okay, so that square distance is the thing that everyone would agree on, regardless of how they rotate the graph.
Exactly. And the intersubjective model becomes a uniform probability density spread across that circle. So it's like saying that all points on that circle are equally likely.
Okay, that makes sense. And what about the individual's own beliefs? How do they fit into this?
Their individual beliefs can be seen as a combination of these uniform densities over different circles, with each circle weighted according to their prior beliefs about the possible values of that squared distance.
So their individual beliefs are like a mixture of these shared intersubjective models.
Precisely. And what's really cool is that if you extend this reasoning to a theoretical limit, you end up with a mixture of conditionally independent, normally distributed quantities.
Oh, wow. So a familiar and widely used distribution emerges from these fundamental beliefs about exchangeability and rotational invariance.
Exactly. It shows how these seemingly abstract statistical concepts can arise from very intuitive ideas about symmetry and invariance.
Now, Wechsler also briefly touches on the concept of exchangeability in the context of infinite sequences and earned schemes. Can you give us the key takeaway from that discussion?
Sure. So, when dealing with infinite sequences of random quantities, Di Finetti's famous representation theorem comes into play.
Okay, this is the theorem that Di Finetti was so proud of, right?
Yeah, exactly. And in this context, it basically says that any infinite sequence of exchangeable random quantities can be represented as if the individual items were drawn independently from some underlying probability distribution, where that distribution itself is random according to your prior beliefs.
Okay, that sounds pretty abstract. Can you give us a more concrete example?
Well, imagine you have an urn filled with red and black balls, and you're drawing balls from this urn one at a time without replacement.
Okay, classic probability problem.
Right. And if you assume that the sequence of draws is exchangeable, meaning the order doesn't affect your beliefs about the proportion of red balls, then your prior beliefs about that proportion must belong to something called the beta family of distributions.
Okay, so the assumption of exchangeability narrows down the possibilities for your prior beliefs.
Exactly. And what's even more interesting is that work by Hill and others has shown that exchangeable urn processes can only be of three types: polyurn schemes, Bernoulli processes like repeated coin flips, or deterministic outcomes.
Wow, so the assumption of exchangeability really constrains the possible processes we can model in this framework.
It does. It provides a strong guiding principle for our statistical reasoning.
Okay, I'm starting to see how powerful these ideas can be. Now, Wechsler discusses Mendel's work on something called inverting the mixture. What's the significance of that contribution?
So Mendel essentially explored whether you could work backward from observed data and predictive opinions to figure out the prior distribution that would be consistent with those opinions.
Okay, so instead of starting with a prior and a model, you're starting with your predictions and then figuring out what prior would lead to those predictions.
Exactly. And he saw the likelihood function, which describes the probability of the data given a particular parameter value, as an operator that transforms prior distributions into predictive distributions.
Okay, so the likelihood is like a bridge between our prior beliefs and our predictions.
Yes, and the posterior distribution, which is our updated beliefs after seeing the data, is like the inverse of that operator. It tells us what prior would have led to those updated
It's like
beliefs.
reverse engineering our
In
beliefs.
a way, yes. And the key takeaway for predictivism is that if your initial predictive opinion is very precise or sharp, it leads to a representation where the forms of both the likelihood and the prior are essentially determined.
So you don't have to arbitrarily choose a prior or a model. They emerge naturally from your predictions.
Precisely. But Wechsler also points out that in practice, we often express our predictive opinions in a hierarchical manner.
What does that mean?
Well, we might start with a general assumption like exchangeability, then add more specific invariance judgments to figure out the form of the likelihood, and finally, our prior beliefs become focused on the parameter that emerges from this process.
So it's like building up our statistical understanding step by step based on our beliefs about the data.
Exactly. It's more grounded bottom-up approach than just starting with a predetermined model.
Okay, that makes sense. Now, Wechsler delves into some of the philosophical implications and practical challenges of this predictivist approach. What are the key things to keep in mind there?
Well, philosophically, it's a big deal because it moves away from this somewhat abstract or metaphysical view of parameters that's common in traditional statistics. Instead of thinking of parameters as these inherent properties of the world, predictivism grounds them in our subjective beliefs about observable events.
So it's a more, you could say, human-centered way of doing statistics.
Yeah, I think that's a good way to put it. But there are also practical challenges.
Like what?
Well, eliciting these invariant predictive opinions from individuals can be quite difficult. It's not always easy to articulate our beliefs in such a precise way, and the prior distributions that result from inverting these mixtures might not always belong to mathematically convenient families, which can complicate calculations.
Okay, so the theory is elegant, but putting it into practice can be messy.
Yeah, that's often the case with new ideas in statistics. But despite these challenges, Wechsler suggests that the traditional approach of just assuming parametric models might be losing ground to predictivism.
Why is that? If it's so messy to work with, why is it gaining traction?
He argues that even within Bayesian statistics, it's possible to have a prior and a likelihood that are individually coherent, but whose combination doesn't actually align with your true predictive opinion. Predictivism, by prioritizing those predictive judgments from the outset, avoids that kind of inconsistency.
So it forces us to be more honest about our beliefs, even if it makes the math a bit harder.
In a sense, yes. And he also points out that predictivism is a very general framework. It can even lead to classical models, like those in the exponential family, as natural consequences of our predictive judgments.
Okay, so it's not about rejecting all of traditional statistics. It's about reinterpreting it and grounding it in a more coherent way.
Exactly. It's about building a stronger foundation for our statistical reasoning.
Now, Wechsler also highlights another important contribution of predictivism, the idea of symmetry between the prior and the likelihood. Can you unpack that for us?
Sure. In traditional Bayesian statistics, there's often this perception that the choice of a prior is somehow more subjective or arbitrary than the choice of a likelihood. But from a predictivist perspective, both the prior and the likelihood are equally important components in a representation that describes our overall predictive opinion.
So they're both reflections of our beliefs, just applied to different aspects of the problem.
Exactly. And this weakens a common criticism of Bayesian methods, which often focuses on the arbitrariness of the prior. By showing that the likelihood is just as much a product of our subjective choices as the prior, it puts them on a more equal footing.
Okay, so it's not like the prior is this uniquely subjective element that taints the whole analysis. Both the prior and the likelihood are shaped by our beliefs.
Exactly. And Wechsler then gives a really nice example of how we can derive the Poisson model from a predictivist perspective.
Okay, the Poisson model. That's a classic statistical model used to describe things like the number of events happening in a certain time period.
Right. And Wechsler starts by offering a predictive definition of what constitutes a Poissonian process. And this definition is entirely based on observable quantities.
Okay, so it's grounded in what we can actually see and measure.
Precisely. And the key point is that this definition leads to a specific mathematical representation that involves a mixture of conditionally independent Poisson probabilities, with the mixing distribution reflecting our prior beliefs about the rate parameter.
So the Poisson model emerges naturally from this set of predictive beliefs.
Exactly. And Wechsler stresses that this predictive characterization is actually stronger than just assuming exchangeability. It's a more specific set of beliefs about the data that leads us to the Poisson model.
So different sets of predictive beliefs will naturally lead to different statistical models.
Precisely. And he provides a very clear fact, as he calls it, that summarizes this whole idea. He states that a process is Poissonian if and only if its probability measure can be expressed as this particular mixture of Poisson probabilities.
Okay, so that's the mathematical essence of what it means to be Poissonian from a predictivist perspective.
Exactly. And he then goes on to outline how the proof of this fact involves concepts like de Finetti's law of large numbers and the Poisson approximation to the binomial distribution. So there's a solid mathematical foundation for all of this.
All right, so we're not just hand-waving here. There's rigor behind these ideas.
Absolutely. And the overall point of this example is to show how a classical statistical model like the Poisson distribution can be derived from a set of predictive judgments rather than just being imposed as an assumption.
Okay, so it's about understanding where these models come from, what beliefs they embody.
Exactly. And Wechsler then generalizes this, pointing out that the simple form of the Bernoulli likelihood in the case of binary outcomes is somewhat of an exception.
The Bernoulli distribution, that's the one that describes things like coin flips, right?
Yes, where you only have two possible outcomes. And the reason it's an exception is because the sample space is so simple. De Finetti's representation theorem is primarily an existence result. It tells us that a representation exists, but it doesn't necessarily give us the specific functional forms for the likelihoods.
Okay, so we might need additional assumptions to pin down those functional forms.
Exactly. And he mentions the work of statisticians like Diaconis and Friedman on partial exchangeability, which explores how we can get predictivistic descriptions within more complex families of distributions.
And there's also a connection to the concept of sufficiency, right?
Yes. Wechsler highlights that researchers have explored the relationship between predictivism and sufficiency, showing how de Finetti's earlier ideas about parameters as measures of agreement already contain the seeds of predictive sufficiency.
So it's all connected. These different ideas are all intertwined.
They are, and it shows how deep and far-reaching de Finetti's influence has been on the field of statistics.
Okay, well, this has been a really fascinating deep dive. To wrap things up for our listeners, what are the key takeaways they should remember from all this?
Well, I think the most important point is that de Finetti offered a really different way of thinking about probability and statistical inference. He was critical of arbitrary parameterizations and emphasized the importance of grounding our models in observable data and subjective beliefs.
And this led to the idea of predictivism, which focuses on making coherent predictions based on the evidence we have.
Exactly. And the key insight here is that statistical models can emerge naturally from our predictive judgments rather than being imposed from the outside.
So it's about building our understanding from the ground up, rather than starting with predetermined models that might not actually reflect our beliefs about the world.
Precisely. And this has profound implications for how we interpret statistical results and how we use statistics to make decisions.
Okay, well, food for thought for sure. And before we go, is there a final provocative question we can leave our listeners with? Something to ponder as they go about their day?
Absolutely. How might this predictivist viewpoint change the way you evaluate statistical claims or models that you encounter in your own areas of interest?
That's a great question. It really challenges us to think about the assumptions that underlie the statistical information we're bombarded with every day.
Exactly. And it encourages us to ask, What are the predictive judgments that went into creating this model?
And do those judgments align with my own understanding of the world?
Precisely.
All right, well, that's a fantastic point to end on. Thanks so much for joining us for this deep dive. And as always, if you have other sources or ideas you'd like us to explore, please let us know. Until next time,
Thanks for having me.
bye for now.